that they know how their talk was received. And I'm going to let Dr. Berggren introduce our graduating senior.
All right, well, thank everybody for coming. So this is Campbell Saint-Vincent. You came to TLU in fall 2013, right?
That's right, yeah.
So it was like 1 year before I did. I can remember meeting Campbell at a back to our picnic by the pond. Is that what we call it?
Yeah.
Our very first event. And I remember, I think I was asking you something about just interest in physics. It was like a physics event. And I think you said something like, it's like, well, you might be a little interested in physics, but you're thinking about minoring in it, but you weren't sure, and you were really a chemistry major and all that. So I remember you saying something like that, and so it was good to see that you became a physics major shortly after that, I think, and have done a great job and been a great student. And so I was able to work with Campbell over, let's see, what semester was that? Spring?
Last semester.
It was spring, right? That we kind of put together kind of research project, worked together on some of these things with these quantum field theory calculations, and then now you put together a senior seminar for us, kind of to present the research. So everybody give Campbell a hand, and we'll let you start.
So yes, my name is Campbell Saint-Vincent, and my senior research topic is on the investigation of profile scales to reduce uncertainty for thrust in quantum field theory calculations. So just quickly, we'll go over some outline that we'll talk about in this talk. For background and motivation, we'll discuss particle physics as a whole, and then we'll get into some observables that we're interested in looking at. We don't quite need to know what this means yet, but observables we can think about just a way to characterize what we see in these particle physics. Then we'll jump into discussing the statistics behind probability distribution functions and cumulative distribution functions. Finally, we'll get into profile scales, which really this is the kind of the main topic of this research, and we'll discuss how it's related to uncertainty in our calculations. And then finally, we'll get into results and conclusion. So particle physics, like space physics, really is frontier science. And one way we study particle physics is by looking at interactions that happen in particle accelerators. So probably the most famous one that I'm sure a lot of us are familiar with is the Large Hadron Collider, which is located in Switzerland. This has a circumference of 27 kilometers, so this thing is pretty huge. So in these particle accelerators, we accelerate protons and they have a collision energy of 13 tera electron volts. So if we use Einstein's E equals gamma mc squared to calculate the velocity of the electron or the protons right before collision, we see that they have a speed pretty near the speed of light. So these are pretty incredible speeds of traveling. In these collisions, we are able to then uncover information about like the fundamental properties of these particles. Now, when we're looking at these collisions, we need to be able to make predictions about what goes on, and we need to be able to understand where uncertainty in our calculations come from. So probably the most popular result from the LHC was the discovery of the Higgs boson in 2012, where experimentalists found that the mass of the Higgs boson is 125 giga-electron volts, but we wouldn't have known to look for this unless theorists had previously predicted a mass be around 126 giga-electron volts. So, some of us might be thinking, like, if this is theoretical, like, we can't see what's going on in these colliders, how can we make predictions? How can we know where uncertainty comes from? Many of us are familiar with experimental uncertainty, where, like in the lab, we have equipment that has, we make measurements, we have propagation of error due to uncertainty in the equipment. But we do make theoretical predictions all the time, and particularly we do this in freshman kinematics. A lot of times when we're solving for systems, we might ignore forces like air resistance or friction, and so the answer that we arrive to isn't really our true answer, it's just an approximation. So if we were interested in understanding the uncertainty in our calculations, we might then try to figure out how much of an effect air resistance or friction would have on our system. So in quantum field theory, our calculations are not perfect, so we need, our understanding is not perfect, so we need calculations to be able to predict our results, and we need to be able to understand where our errors come from so that we can decrease them. Now in these particle accelerators, we have a set of observables that we're interested in, and one way we can kind of think about this is in classical physics, something we might be interested about is like the total energy of a system or where our final position might be. Particle physics is a little bit different. There's a lot of complicated things going on, so we do have a set of observables that we look at that tell us useful information about what goes on. So the first observable that we'll discuss are jets, and these really are just tight clusters of quarks, gluons, antiquarks that result in these collisions. So we see in this Feynman diagram that in an electron-positron annihilation, the energy is converted to a photon, then that photon is split into a quark-antiquark pair, and then those quark-antiquarks are split off into more lower energy quark, antiquarks, and gluons. And when these split off, they are clustered tightly into what we call as these jets. So more specifically for this research, the observable that we're doing our calculations on is thrust. And we can think about thrust as similar to jets. Most simply put, we can just kind of think about thrust as a way that it tells us how much a certain event looks like we have two jets. So we can imagine that if we have really small thrust values, we have tightly clustered jets, two tightly clustered jets that would give small thrust values. For large thrust values, our thrust, we have more than two jets. We don't necessarily know how many more, we just know our system looks like we have more than two jets. And then if our clusters aren't really tight, like it looks like we have two jets but they're not tight, tau might not be small. So this is kind of an interesting thing you might want to think about. Now ultimately, the theory behind these observables, we don't need to get too concerned with because the method for reducing error that we'll talk about can really be applied to hundreds of observables, really anything we're interested in. So now before we get into more in depth in the research, we just need to have a quick discussion on what probability distribution functions are. So highlighted in blue, we have our probability distribution function. And we can think about on our x-axis is like an observable we'll be interested in. So we can think about if we were going on a trip and we were sampling or we were taking measurements of our velocity at any time during the trip. Let's say we picked 20 meters per second. Well, the PDF would tell us it's 5%. So 5% of the trip we're traveling 20 meters per second. Now our cumulative distribution function is related to the PDF in that it sums for any value on the CDF, it sums all values on the PDF before. So it's just a shaded region. You're integrating over the PDF, so it's just a shaded region underneath. So we could think about for the same trip, if we pick 20, it's 80%. So 80% of the time we're traveling 20 miles an hour or below. So it's accounting for all the ones below it. So in our quantum field theory calculation, we have one calculation that is dedicated for obtaining our PDF, and then we have a separate calculation, independent, that is dedicated for obtaining our CDF. So we can also get to our PDF by an indirect method, which we can take the derivative of our CDF, or you get to the CDF by taking the integral of our PDF. So when we're thinking about what's going on in what we want to do with decreasing uncertainty, we want to reduce error in our calculations and we want to maintain trustworthiness. So what I mean by this is if we had on the left here a bunch of calculations where these different colors indicate higher orders in our calculations, so we can think about like a power series. Each order in our power series, we should get a better approximation of our true answer. So if in yellow we make a calculation at a low order, we might think our true value would lie somewhere within that band. But then if we go another order higher and we get this purple band and it's shifted way away from our yellow band, well now can we trust that yellow band? We don't know, and then if we keep increasing the order, maybe our bands keep shifting up. So we can't trust that our true answer is within really any of these bands. So what we want to make sure that happens in these calculations is that we want to, in higher order calculations, not only decrease the error, but also make sure these bands converge so they're within each other. So we have better reason to believe that if we were to take more higher order calculations, our true answer should still be within those bands. So now in the quantum field theory calculation, we have this parameter that shows up that we call mu, and it's really non-physical. It shouldn't be there in our power series, but it is there. And if we were to take every term in our power series, which we can't do, mu would cancel out. But it doesn't. We can only take so many terms in our series, so we need to pick sensible values for this mu. And we can see that when we're calculating for thrust from quantum field theory, that mu is dependent on thrust. So for different thrust values, we would pick different mu values. And we want to just kind of estimate the size of mu. How much does mu affect our calculation? So we might think about thinking back to like air resistance or friction. If we had an answer that we found and we were maybe to pick sensible values for air resistance, like a lower and upper value, that would tell us kind of how much of an effect air resistance would have on our calculation. We kind of think about the same thing with this mu. So then when we use the mu, the profile scales, 9 different variations, we use it to calculate our PDF. We get 9 different unique probability distribution functions from those 9 different mu's that we had before. So our uncertainty is just the envelope of those 9 calculations that we have. And then in another calculation for calculating the CDF from our cumulant method, which is dedicated to the CDF, we get another 9 unique CDFs. So what we notice in this is that it's a little, as we get to higher values of thrust, our error shrinks quite rapidly, so we can't really see what's going on here. So when we move on to looking at new plots, we're going to split this up into 3 regions. We're going to have a peak region, a transition region, and a tail region, so we can kind of see better what's going on. Now there's a lot going on in these couple, these plots here, so we need to really make sure we understand what's going on. In the top plots that are PDF, we can see that we have split this up into 3 regions, so this is identical to the plot we showed before. The black band is our dedicated calculation for the PDF. So this is the one that we trust, and we see that in the peak region there's high uncertainty, there's large error, but as we get to the transition and tail region, that error shrinks quite rapidly. And then the green band is the PDF that we get from taking the derivative of our dedicated cumulant CDF. And then on the bottom we have our CDF. The black band is going to be from the standard methods. We take the integral of our PDF, and that gives us this black band. And then the green one is the one we trust. This is the one that's dedicated for this calculation. So one thing that we notice is that in this peak region, the green one that we trust has very low uncertainty. So what we want to do is get information from the PDF in this region, or the CDF in this region, and that has low uncertainty, and try to decrease error in our PDF in this peak region with high uncertainty. So the way we went about doing this is we went back and looked at our original scales, the 9 variations of scales we had, and we just picked out one type, or one scale, we'll call it mu-s. So it has an upper and lower bound to it. And so these were scales that had been previously, or variations that had been previously created from past research. So what we wanted to do is figure out what effect this scale had on our the uncertainty in our PDF and CDF. So what we did is we made a new set of variations from the mu-s, and we interpolated between the upper and lower bounds. So we made a new set of 9 scales, or 9 variations of the scale, and then we went and used this to recalculate our PDF. So we recalculated PDF. We now see 9 different unique CDFs from those 9 unique variations that we just made. And then remember, in green, this is the one that we trust. So what we did then is we did this process again. We picked the one that lies very close to the green one, and then we made a new set of scales from that. So this is like a second time doing this interpolation process. And it's a little hard to see, but this would be that scale that would create the PDF that was very close, or the CDF that was very close to the green one. So we have a new set of 6 variations of the scale we made from this mu-s. And then we just went back and we did the same process with all the other variations of scales we had. I won't go into too much detail with this, but it's just the exact same thing that we did. And then we made a new set of CDFs from those other scales. So then what we did is we took all of it, we put it together, we wanted to figure out how this compared to our previous methods. So again, in black, this is the plot that we saw before for the PDF, the one that we trust. That's with the original 9 variations that had already been previously made. So that's the one we trust. The blue band is taking all those scales, those new ones that we just made, and recalculating our PDF. So what we noticed is that not only does our error decrease, which is what we wanted, but also the band is still within the one that we trust. So we don't know necessarily if our true answer was within the blue band, but from these results we have an indication that we might be able to trust this, because if the blue were to be completely outside this black band, we wouldn't necessarily trust it. So this is a good indication here. And then what we did is we took those same set of scales and then we recalculated them for all orders in our from quantum field theory. So this is the original set that we had from the 9 scales, and we see that as we get from the peak to the tail region that we have convergence in our bands, and also the error is decreasing. But then when we look at our new set of scales, we still do maintain convergence among higher orders for our transition in our tail region. However, what we do notice is that in this peak region, the bands are not converging. Even though the error has decreased, the bands don't converge. So we might not necessarily take this at face value that this is untrustworthy. And when we did these calculations, we only did a small number of steps in our calculations. So if we were to increase this, we might actually see that this peak region, we would have better convergence. So then just kind of summarize what we did in this research. We are able to create a new set of variations of our original profile scales using the cumulant CDF as a guide, because the cumulant CDF has very low uncertainty in tail regions. And then using our 4th order calculation in quantum field theory, we were able to create we calculated a new set. And then what we did is we were able to show that we did reduce error and we shrunk the uncertainty in transition tail region for our standard PDF, or our standard PDF. Our peak region may not be untrustworthy, as we saw, because if we took more calculations, we might see that our errors converge. And then for the future, I would like to look at using new scales. We're creating a new set of scales from different orders. So instead of just using the 4th order calculation, look at the other orders that we have in quantum field theory and create a new set of variations from these. So then some acknowledgements I would like to make. Texas Lutheran University Physics Department, I'd like to thank Dr. Berggren. He was my advisor on this research topic, and I would like to thank Dr. Sansi for all her help.